Hello everyone, thank you for attending my presentation. My name is Zhong, a PhD student from the University of Tennessee. The topic of my presentation is using ARM Scalable Vector Extension to optimize OpenMPI. This is a joint work of the University of Tennessee, ARM, and also Fujitsu. Here is the outline of my presentation. The first one is the overview and background of this work. The second part includes the design and analysis of our proposed work using ARM SVE for optimization. Then I will talk about extended implementation into OpenMPA and also the experiment evaluation. Finally, the conclusion of this paper. I will give more details about those work one by one in this presentation. At the very beginning, I want to mention this is a collaboration work of UTK ARM at Fujitsu. ARM provides the opportunity to explore SVE features from the new ARM v8 architecture and also the test and experiment platform. Fujitsu provides early access to the new ARM-based processor A64FX and also helped conduct the tests. This work mainly contains three parts. The first is a detailed introduction about ARM SVE and also related tools, including ARM AE, which is official instruction emulation tool. The second part is the GIMP5 evaluation. The last part is the implementation in OpenMPI and also the evaluation. Here's a brief introduction about ARM SVE. SVE is a separate architecture extension with new sets of instructions. It does not define sets of vectorless. Instead, it provides different vectorless values ranged from 128 bits to 2K bits, which will be automatically selected at runtime. This extension is a similar concept of Intel AVX, but with longer registers. Intrinsics are C or C++ function calls that the compiler replaces with appropriate single instruction multiple data instructions. ARM provides the ARM-C language extension for SVE. It provides the function to instruction mapping of SVE vectors and predicates, and the functions interface for relevant SVE vectorization instructions. It also enables high-level language users to explicitly use the data types and operations available in ARM SVE ISI. ARM introduced ARM v8 based architecture, which includes ARM's law vector extension, SVE. We want to use law vector extension to optimize reduction operation and also pack operation. When we did this work, there is no hardware. We used internal tools provided by ARM to test and evaluate our design and implementation. Without any hardware support for SVE instructions, we had to use a tool called ARM AE. This tool will emulate SVE instructions and also can help us to calculate how many instructions need to be executed. We evaluate the performance of our implementation by comparing the number of instructions that are executed. However, this raises a problem. Does less instructions equal to shorter execution time? GIMP5 Simulator is an open source modular platform for computer system architecture researchers, which can be used to calculate actual cycles that need for the execution. We will also use this tool to evaluate the performance of our work. ARM SVE provides a lot of novel features that can be used for high-performance computing. And we are interested in two major features. One is the rich memory access feature, and the other one is the law vector reduction operation feature. Rich memory access including using multiple vectors to load and store for contiguous data, and also using gather scatter with non-contiguous data. For the reduction operation, it provides a valuable set of reduction operations for logic and mathematical reduction operation. For any type of communication, including point-to-point and also collectives, before sending the message, users need to pack the message in the setting buffer. There are two types of data and memory layout. One is contiguous data type and one is non-contiguous data type. Here we introduce using multiple vectors for load and store. For a general mem copy, it uses single vector for load and store, but using ARM SVE, each instruction can use up to 4 registers to load and store. This right figure shows the assemble code for those two cases. We can see that the non-SVE version of memcopy, it uses 1 vectors for load and store, but for the SVE-enabled assembling code, it uses 4 vectors to load and store for each instruction. The second case is for the non-contiguous data type pack and APAC. To deal with non-contiguous pattern, the general implementation is that it uses the for loop to do a mem copy for each of those non-contiguous chunk. But by using gather and scatter feature, we can provide offset of each non-contiguous part. As then a single instruction can gather several segments based on the provided offsets. And for the unpacking, we can use scatter to distribute the data to a non-contiguous pattern. Here are the 3 mainly used non-contiguous data type in MPI. The first one is called vector type, which is described by a fixed block length and also fixed thread. The second one is called block index. Neither the size of each block nor the displacement between successive blocks are constant. The last one is called index type, which normally describes a column or a matrix. Those non-contiguous patterns need to be packed to a contiguous pattern before setting. Here is a comparison for contiguous memory copy operation using memcopy and SVE-based memcopy. For general memcopy, it uses 1 vector per instructions to load and store. For SVE-enabled memcopy, it uses 4 vectors for each instructions to load and store. The left plot shows the instruction count of those two cases. We can see that by using SVE-based memcopy, we decreased the instruction count by 4 times. The right plot shows the corresponding Gen5 timing information. We can see that we reduced the execution time by 5%. This is because that memory copy is a memory-bounded operation. And for both cases, it achieved the peak performance. Just by reducing number of instructions, we achieve 5%, which is still very expressive. This slide shows the performance comparison of non-contiguous pack and APAC. Same as before, the left figure shows the instruction count. By using SVE gather and scatter, we reduced instruction count by 10 times to 100 times as the vector length increases, because with larger vectors, you can gather more elements into one single register. And the red is the Gen5 result, which shows a performance benefit of 20%. It should be more obvious. The reason behind this slowdown is that the SVE support in Gen5 is not quite efficient. In this section, we will show the design of the reduction operation. First, we see the difference between a scalar operation and a vector operation. The left plot shows the scalar operation, addition operation of 2 buffers. We can see for every time it deals with 1 element, but the right plot shows the vector addition operation on 2 buffers. We can see each instruction can process multiple elements instead of 1 for same amount of data. vector operation need less instructions. And we use Arm's law vector reduction operation. We can see the vector length is up to 2K bits, which can deal with 64 integers with Z, a single instructions. Here is the comparison of SVE and non-SVE reduction operation. We can see the left plot shows 60% performance benefit of instruction count. And the Gen 5 result shows 30% performance benefit. Also, we can see as the vector length increases, the execution time decreases because for longer vector, it can deal with more elements per instruction. We extended our design and analysis to the implementation of OpenMPI. We use multiple vector load and store for contiguous data type, pack, and unpack. We use gather scatter feature for non-contiguous data type, pack, and unpack. Last but not least, we use log vector reduction instructions for MPI reduction operation. We added those features to different components and modules in OpenMPI. We added it to data type, pack, and unpack, and also reduction operation. We asked people from Fujitsu because they are the only people that have early access to ARM-based A64FX chip. We asked them to conduct experiments for our design and implementation. This slide shows results for pack and unpack optimization. The gray and yellow line indicates the performance using vector length 256 bits and 512 bits respectively with our gather and scatter strategy. Compared to the default MPI, which is the blue line that is not using gather scatter feature, we can see that our optimized algorithm is 2 times faster than default OpenMPI. Here is the result for reduction operation or A64FX. We flushed cache in order to make sure we are not reusing cache for a fair comparison. We can see the SVE-enabled reduction operation is 4 times faster than the element-wise operation. We also compared our SVE reduction operation result with memcopy operation. Because memcopy will indicate the peak memory bandwidth. And for a reduction operation, it needs 2 loads, 1 store, and also a computation. But for memcopy, it only needs 1 load and 1 store. Here we can see, even with computation included in our SVE reduction operation, we achieve a very good performance. Here is the conclusion of this work. First, we provide detailed analysis of SVE log vector instruction. Also, we extend the design and implementation using memory access instructions and also reduction instructions to optimize OpenMPI. We demonstrate the performance benefit of our implementation using ARM AE and also Gen 5. And also, we conducted experiments on Fujitsu's ARM-based processor AF64X shows very good performance. That's all. Thank you.